Hi, I'm Lior, and I want to talk to you today about robust quantum entanglement at nearly room temperature. Okay, so let's recall Schrodinger's cat. So we've all heard about this near-death experience of a thought experiment feline. The way it's usually stated as you have a cat which is entangled to a poison vial, in the sense that if the poison vial is unbroken, the cat lives, and if the poison vial is broken, the cat is not so fortunate. So this is a textbook example on how to explain entanglement, but actually it is a cynical view of entanglement. This is Schrodinger's way of telling us that we're likely to see or encounter large macroscopic scale entanglement as much as you can entangle a cat to a poison vial. But the question is this cynicism true? So when in doubt, we blame decoherence, right? We blame decoherence for everything. So what is decoherence? You start with a nice clean pure state that you want to use, say, the initializing state for Shor's algorithm, and then you couple it to a heat bath, an auxiliary system to which you have no access to. This is the world outside, right? And then you let it thermalize and reach some equilibrium. And decoherence, what it causes uncontrolled thermalization, and it's usually cited as the root cause that we are still not selling quantum computers by the dozens. So now, if we compare theory to real life, ideally, we'd like to manipulate pure states on many qubits, but in reality, we're unable to do so. So we're unable to retain purity as the number of qubits grows and the temperature increases, so we only get mixed states. So physically, in fact, there's actually just kind of one relevant mixed state. It's the thermal state. It's e to the minus beta h over z, where beta is called the inverse temperature, is 1 over kappa T, where T is temperature and kappa is the Boltzmann constant. And here H is some Hamiltonian of your choice. In other words, this is a distribution, you can think of this as a distribution on eigenstates, where each eigenstate is sampled with probability, which is e to the minus its eigenvalue times beta. Okay, so let's go back to our previous question. Can we see entanglement at room temperature? Well, now the question in this form should be, can you design a local Hamiltonian, H, such that its thermal state, to the minus beta H, is entangled? So this would be corresponding to, say, having a cat entangled to something, right, at macroscopic scales. So how can we test for something being entangled if it's a mixed state? Well, it's hard to quantify, even for pure states. So instead we use here a proxy, which is quantum circuit lower bounds. So here's a local quantum circuit. It is a product of d such unitaries, 1, 2, up to d. And each layer is a tensor product of, say, 2 local unitaries acting on pairs of qubits. And you have these layers maybe working on different subsets of pairs. And you have d such layers. And now you can define circuit complexity. Circuit complexity of a state rho is the minimal integer d for which there exists such a unitary circuit U, that if it acts on the all zero state, which is completely unentangled, and then you may be tossing away some of the qubits, you can approach your target state to some vanishing phase distance. So for any state rho, we have a circuit complexity, which is some integer d. So now our main conjecture using these notations is called robust topological order at room temperature. We ask whether there exists a local Hamiltonian H on n qubits that is both topologically ordered. In other words, it has a highly entangled ground state. And even for some beta, which is O of 1, the thermal state has high circuit complexity. In other words, the circuit complexity of e to the minus beta h is omega log n. The function here is somewhat important because it somehow requires or allows you potentially to couple any pairs of qubits in your system. So, truth be told, if you look at this conjecture, we know of many local Hamiltonians with a highly entangled ground state, right? These are, for example, quantum error correcting codes with large distance, say the Tori code. But yet, we don't know of any such Hamiltonian for which the thermal state at high temperatures retains its circuit lower bound. In other words, for all we know, the quantum error correcting codes, the good ones that we know of, if you raise their temperature, the Hamiltonian, by a little bit, you may get something which is completely decoherent. as a thermal state. In other words, you may be able to simulate this quantum state to arbitrary precision using very shallow circuits. The conjecture asks whether you can somehow prevent that. And our main theorem is that this conjecture holds for nearly optimal parameters. In other words, there exists a local Hamiltonian H on n qubits that is simultaneously topologically ordered. And for beta, which is maybe not O of 1, but of log n, right? In other words, the temperature is almost constant, just decays like 1 over log n. The thermal state is high circuit complexity as desired, has the desired circuit complexity. So in fact, we show more. We show that the thermal state of these Hamiltonians is locally decodable to a highly entangled quantum state. So in other words, the circuit low bound that we cite here actually emanates from entanglement, right? So circuit complexity is a proxy for correlation, not for entanglement. It could be the case that, I'm hand waving here circuit complexity lower bounds, but it could be coming from classical correlations, classical long-range correlations. But in fact, we show that the circuit low bounds here are actually coming from proper quantum entanglement. So the take-home message, if you just want to quit the talk right now, is that while we still can summon into a cat poison entangled state, if we allow the Hamiltonians to be local, but not spatially local, so to allow these Baroque mathematical constructions, we can get quantum systems that are, on one hand, truly quantum at zero temperature. They are topologically ordered, and yet their entanglement persists at very high temperatures, decaying only very gradually with system size. Okay. So let's think about this for a second. How to entangle things robustly. So let's recap. Our high-level goal is as follows. We try to formulate a local Hamiltonian that has a highly entangled ground state, and we want its thermal state at temperature T to be assigned circuit low bounds for all sufficiently small t. And we'll show something stronger, that the thermal states are in fact highly entangled. It's not just a circuit low bound. So here's the main idea. So we can get quantum circuit low bounds for free, kind of for free, from quantum error correcting codes. And this is kind of a folklore result that essentially uses the fact that any two orthogonal code states are undistinguishable by any local measurement. This kind of implies that for sufficiently small error, you can't do this for any shallow circuit. And we want to make these low bounds stick for high temperatures. And now this is non-trivial, right? So the way we do this, we demonstrate a shallow, no-depth decoder from the thermal state to the ground state. In other words, for any sufficiently small temperature, you consider the thermal state, and you show that by applying a shallow decoder, you can get back to the ground state of the Hamiltonian. And then you can conclude the circuit low bound survives for the thermal state, simply by subtracting the depth of the shallow decoder. So, in other words, the entire focus of this talk would be to demonstrate a shallow decoder from the thermal state to the ground state. And this would kind of conclude the proof. So here's the main problem to doing this. Thermal state is defined in terms of energies, right? It's a distribution corresponding to value of energy. However, once you consider local decoding, essentially you need to know something about errors. So how can we translate from one regime, which is physically motivated, to another regime where we have all the technology for error correction? So we need to change regimes. So let's talk about the thermal state again. So for sufficiently small t, if you plot down the energies kind of schematically, or with high eigenstates here and low eigenstates here, you can think that for sufficiently small t, most of them are concentrated on the cool side. Maybe there is some tail going into the high energy states. And then you can talk about the regime of errors. You can think about regimes of errors where there is large weight errors, and places where the errors have very, very small weight. Okay, so essentially your kind of desire would be to have this map between high energy states and high weight errors and low energy states and low weight errors. And the way to do this, in fact, I think the only way to do this would be to use kind of quantum locally testable codes that do this kind of by definition. So I'm not going to cite here the formal definition, but essentially, quantum locally testable codes are a generalization of classical LTCs in the way that they penalize any error according to its Hamming weight or distance from the code space. Okay, but unfortunately, this is still not enough, right? Even if you can leverage quantum local testability to force the errors to have low weight, they could potentially form large clusters. And this happens because the regime of temperature that we consider here, the beta, the temperature is pretty high. In other words, you can, for T's we consider, you can get clusters of size n over log n. This is like way beyond your error correction capability. And you may, in that situation, you may not be able to do even shallow decoding. So we need something more. We need the error weight to be actually very, very sparse. I mean, like you want errors to kind of break away to these small clusters, because in that regime, you can actually hope to have a shallow decoding scheme. So now we can't kind of kick the can any longer. We somehow need to tackle this problem head on. So now we consider the thermal states, and we want to analyze it in terms of errors. And the way we do this is we redefine the thermal state as a random process. It's called the Metropolis-Hastings algorithm. And it formulates this as a random error model E, where an error E occurs with probability that is comparable to the additional penalty it introduces. And then what you can show that if you let a system reach its equilibrium under a local Hamiltonian, which is derived from a quantum LTC with constant soundness, then its stationary distribution has typically small clusters. So formally, we say this: if C is a quantum LTC with constant soundness and rho is a thermal mixed state, under this e to the minus beta h of C, then if you look at a typical error, then its maximal connected component is logarithmic. In other words, for sufficiently small t, which is 1 over log n, the quantum local testability property forces the errors to be very, very well spread out. And this is a crucial component. So now let's recall again the required ingredients. So we need a quantum error correcting code to kind of gain the folklore result of circuit low bound at 0 temperature. We want the code to be a quantum LTC with constant soundness. And now the final component is that we want to be able to locally correct sparse errors, right? We said that QLTC brings us to the right regime. And now we want to be able to invoke a shallow decoder to get the job done, to get us back to a code state from the thermal state, say by applying some quantum variant of the Sipser-Spielmann decoder. So now a sufficient condition for this is that the Tanner graph of the QLTC is locally expanding. In other words, if you look at small subset of qubits S, then the number of check terms incident on these subsets is almost optimal. It's almost S times the degree, the maximum degree of each qubit. Okay, so this was the ingredients. Now let's talk about the recipe. So let's bring this to an actual recipe. So we start with the best quantum LTC to date. It's called the Projective Code by Leverrier, Lone, and Zemmour, and it's actually in this conference. It's a paper here. And then we amplify it to constant soundness. This by just taking random family of subsets of check terms. And then we consider its topology for small subsets. And in fact, we show that it is locally expanding for small sets. How small? As large as we need, right? So we only care about subsets of size log n, and then we show that for such size, which is very, very small, the expansion is very, very good. What we get here is something which is like epsilon is like 1 over 16. In other words, you locally expand almost like a tree. Okay. In other words, we're interested only in the regime where S is very, very small. Typically, if you talk about the Sipser-Spielmann decoder, you would be interested in sets S of size which is linear in n, but here we are always in logarithmic size. Okay, so to summarize, we've shown that quantum thermostates governed by a Hamiltonian, which is QLTC, have, for sufficiently small temperature, sparse errors. Okay. Now, in addition, if these codes are locally expanding in the sense that we've just said, in terms of the Tanner graph, it means that we can kind of correct these errors using shallow circuits and get back to the ground state where we can claim our large circuit low bound. So this means that the thermal state itself for such Hamiltonians is highly entangled in a well-defined way. Okay, so that was a technical summary. So in conclusion, we can say that macroscale entanglement can persist at nearly room temperature. So maybe as a kind of final statement, you can say Schrodinger's cat is possible, but maybe perhaps under a new name, perhaps Schrodinger's projective cat, which I drew right here. Thank you.